When a machine learning model hits 99% accuracy during training, it looks like a success. But if that same model fails the moment it interacts with real-world data, you're likely looking at a failure of generalization. This is called overfitting. It happens when the AI doesn't actually learn the underlying patterns of the data, but instead memorizes the random noise and unique coincidences present in its specific training set. This chart illustrates the mechanical cause. The model has assigned massively inflated mathematical weights to its features. These weights are multipliers, determining how much influence an input has. By making these numbers extremely large to hit every data point, the model becomes highly unstable. To fix this, we forcefully constrain the AI. We tell the model to fit the data, but restrict its ability to make dramatic, hyper-complex adjustments. Solving the overfitting trap requires a strict mathematical boundary. By forcing the model to prioritize simplicity, we can prevent it from being misled by the noise in our training samples. That boundary is created through regularization. It works by adding a penalty term to the model's loss function, the mathematical formula used to measure error. This penalty actively pushes back against complexity. This chart shows the trade-off. The model must balance two competing mathematical goals simultaneously. As the AI minimizes prediction error on top, the penalty term forces it to keep mathematical weights small. This prevents any single feature from having an unstable influence. Data scientists control how aggressive this penalty is using a parameter called lambda. When lambda is increased, the penalty grows heavier. This forces the model to shrink its weights, which might slightly reduce its accuracy on the training data, but makes the model much more stable on new data. However, if lambda is set too high, the model becomes too constrained to learn the actual patterns in the data. This results in underfitting, where the model is too simple to be useful. The lambda dial acts as the toggle between a model that memorizes every outlier and one that identifies broad, repeatable trends. It is the mathematical bridge between training data and generalized intelligence. There are two primary formulas for applying this penalty. The first is L1 regularization, commonly known as lasso. Lasso is the least absolute shrinkage and selection operator. It calculates the penalty using absolute values of the coefficients. As the penalty increases, lasso pushes less important feature weights exactly to zero, effectively removing them and leaving only the most significant variables behind. This automatic feature selection is particularly useful in business settings. It allows stakeholders to identify the 3 or 4 primary drivers in a dataset that might contain hundreds of noisy or irrelevant variables. The second formula is L2 regularization, known as Ridge. Unlike lasso, Ridge uses the squared values of the coefficients to calculate the penalty. Notice the difference here. Ridge doesn't erase features, it shrinks all of them proportionally toward zero. Every feature remains in the model, but their influence is collectively dialed down. Ridge is the better choice when your data has highly correlated features, like a house's square footage and its total number of rooms. Instead of arbitrarily deleting one, Ridge balances their influence to provide a more stable prediction. In short, lasso is used to eliminate irrelevant noise to find essential variables, while Ridge is used to manage complex interconnected data without losing the context of the secondary features. If you need both capabilities, you can use ElasticNet, a hybrid approach that blends the feature elimination of lasso with the stability of Ridge. This leaves us with the practical challenge of locating the exact numerical value for lambda. We need to find the setting that yields the best performance on a dataset the model hasn't seen yet. Cross-validation tests different lambda values. The vertical axis tracks validation error. As lambda increases, error drops, stopping overfitting. It hits its lowest point here, the optimal value. Increasing the penalty further raises the error again, causing underfitting. Modern coding libraries allow us to automate this search quickly. This has made regularization a default step in nearly every professional machine learning pipeline. By intentionally limiting a model's complexity, we ensure the algorithm relies on the broad, repeatable patterns rather than the specific noise of its training environment. This restraint is what makes the resulting predictions reliable when they move from the lab into the real world.